Okay, welcome back. Let's look at some properties of the expectation. Expectations are linear functions, and linear functions we understand very well. First property, when x is integrable, that is equivalent to, in expectation, x absolute value is finite, and that is equivalent to in expected value of x plus is finite, and the expected value of x minus is finite, resulting in the fact that the expected value of x is finite. Secondly, when x omega is less or equal to y, almost surely, and that stands for this expression over here. So written out in detail, it's over here, probability. The probability that omega in big omega, that x omega is less or equal y omega is equal to 1. Yeah, and when x and y are integrable, then the expected value of x is less or equal than the expected value of y. And in particular, if x is equal to y almost surely, then the expected value of x is equal to the expected value of y. That is the monotonicity condition. And these conditions, they are listed here without proofs. The proofs are in the book, and they are not that hard to show. Yeah. So the first one, expectation being finite means that x is integrable. And to guarantee that if one looks at the absolute value, this has a finite expectation, then the original also has finite, exists. Yeah. And in the general case, one works with x plus and x minus, of course. The third one is the linearity one. So it's a linear function, as I already mentioned. So the expected value of alpha x plus beta y, alpha and beta equals real numbers, is equal to alpha expected value of x plus beta the expected value of y. And the last one, Jensen's inequality, a very useful one also in practice and often in finance. So if we have a function phi, which goes from R to R, and it's a convex function, and convex function means what is written over here. So this is the definition of a convex function. Phi with as argument ax plus 1 minus a y, where a is between 1 and infinity, that is less or equal to alpha a times phi of x plus 1 minus a times phi of y. So when phi is a convex function, then one can show a very useful property that the function phi of the expected value of x is less or equal than the expected value of phi x. So the function of the expectation is less or equal to the expectation of the function. And here we have a very interesting and handy example. If we, for example, choose phi x being x squared, and we use that property 4, then this gives us that the expectation square is less or equal to the expected value of x squared. So the square of the expectation is less or equal to the expectation of the square. And if we look at this a bit deeper and we remember the definition of the variance, we see that this actually tells us that the variance is always positive. Yeah. All right. Let's start with the slide number 17. So there are properties of the Lebesgue integral. And as you saw, the Lebesgue integral, you know, to get the value, you have to go through a process. You have to split your random variable in x plus and x minus. And for x plus, you approximate it with an increasing sequence of simple functions, the way we did it, with partitions. And then you take the expectation of this, because you have it well defined. You know what it is, and then you take the limit. So in practice, computing a Lebesgue integral is a long process. But what is actually nice is if we look at Lebesgue versus Riemann on this slide, and in the case of the Riemann integral, we have all these formulas and you know how to integrate. Now, luckily, and in all our applications, this will be the case, we are able to integrate. Yeah, and so if we compare Lebesgue versus Riemann, and we have the following. So if f is a function from an interval, a closed interval a, b to r, and it's a bounded function, which is Riemann integrable, then f is Lebesgue integrable. And in detail, the integral from ab fx dx, and that's the Riemann part, is equal to, and we write it like this, the integral over the interval of fx d lx, where L is the Lebesgue measure. And so your domain is AB, and you have the Borel sigma algebra and the restriction of the Lebesgue measure. So we put it, we call it calligraphed L here, right? And that is, we have the Lebesgue measure, and the Lebesgue measure of an interval is just the length. And in this particular case, we can integrate the way we are used to. So in fact, this is equal to the expected value of f. And we have used just a function f. And because it's general, we have denoted it by f. Yeah, and in many cases, we are dealing with a sequence of random variables, and they converge to some random variable. Say we start with xn, and they converge to x. And the sequence need not be monotone or anything like this. And we would like to see when is the limit of the expectation of the limit. And this is not always true. One has to check certain conditions. And there are theorems that tell you when you are allowed to do that. So let's look at these theorems. Yeah, they are important theorems, and we will not prove them here, but we refer to the book for the proofs. And also on the slides, there are some proofs. So if you just look at the slides, then you can also study the proofs. But in principle, I would like to refer to the book for that. So these are limit theorems. And they have consequences for the integrals and the expectations. Let omega fp be a probability space, and let xn be a sequence of random variables, and x be a random variable on omega. And then we say that the sequence xn converges to x almost surely if the probability for an omega in x, such that in limit n to infinity, xn of omega is equal to x of omega is equal to 1. And this is pointwise convergence. It doesn't have to hold for all x, but it does hold on a set of measure 1. Yeah. And then the question that arises is, suppose we have a sequence xn that converges to x almost surely. Does this also imply that the expected value of xn converges to x? And the answer is no in general. Yeah. So we need extra conditions. Yeah. Consider space 0, 1, the interval, the Borel sigma algebra on 0, 1, and the Lebesgue measure, where we know, of course, that the Lebesgue measure of an interval is just the length. And as an example, a counter example, think of xn of omega being n times the indicator function on the interval 0, 1 over n, omega. Now, if we see if I can plot it here somewhere, maybe down here. So what do we have? We have our axis here. We have 0, 1. This is 0. This is 1. Then here we have our 1 over n. 1 over n. And here we have our n, right? And when n grows, this interval gets smaller and this value gets larger and larger. And this is the sequence xn. Yeah. And of course, we see that when xn goes to 0, when n grows and grows and grows. So x, the value it converges to, is just 0. Yeah. However, if we look at the expectation, the expected value in this case, the expected value of xn is just the probability times the value, right? So it is the value n times 1 over n. So that is equal to 1. But yeah, because x is just a 0 random variable, then the expectation of x is equal to 0, and they are not the same, right? They are not the same. So here you have a counterexample indeed. So the expected value of the sequence is 1, and that is not equal to 0, which is the expected value of x. So when is it then the same, right? No in general, but when is it the same? The question, under which conditions do we have that in limit n to infinity, the expected value of x sub n is equal to the expected value of x? The first theorem tells you that this is possible. It's an important theorem. But as you see from the name, monotone convergence theorem, and we abbreviate it often on the slides with MCT. And in the book, this is theorem 145. Yeah, we have to require monotonicity. So the sequence should be a monotone sequence. Yeah, non-negative and increasing. So suppose xn converges to x almost surely, and x1, x2, etc. form a non-increasing, a non-negative increasing sequence. If we have that, then this monotone convergence theorem tells us that in limit n to infinity of the expected value of xn is equal to the expectation of the limit n to infinity of xn is equal to the expected value of x. So the limit of the expectation is equal to the expectation of the limit is equal to the expected value of x. Yeah, and as an example that we all know, suppose x is discrete and it takes an infinite number of discrete non-negative values, then we know from the definition that the expected value of x in this case is the sum over I of xi times the probability that x is equal to xi. And this follows, in fact, from the monotone convergence theorem. Let's define xn as the sum of I is 1 to n xi times the indicator function for x equal to xy. Then if we look at it, we see that xn converges from below to x, and xn and x are non-negative. So the expected value of x is then equal to the limit n to infinity of the expected value of xn. And we write this out, this is in limit n to infinity, the sum of I is 1 to n of xi times the probability x is equal to xi. And this is indeed, when the n goes to infinity, this is the sum from I is 1 to infinity of xi times the probability that x is equal to xi. And that is indeed the definition of the expected value of the discrete non-negative values. Now, this theorem, the next theorem, the Lebesgue-dominated convergence theorem, which is in the book theorem 1.4.9, that is even a bit more general because monotonicity is dropped. But monotonicity is dropped, but it has to be replaced by something, namely the boundedness of the integral function. Yeah, and this convergence theorem goes as follows. Let the sequence xn exist, and moreover let y be non-negative, so and integrable, so let xn and y be integrable and y moreover be non-negative random variables on a probability space omega fp, and x a random variable on omega satisfying the following conditions. The sequence xn converges to x almost surely, and not necessarily monotone in this case, right? And instead of that, we have the requirement that in absolute value, xn should be less or equal to y, almost surely, for all n. So that is the boundedness condition. And then this theorem says that x is integrable, meaning that the expected value of the absolute value of x is finite. And moreover, the expectation of x is equal to the expectation of the limit of n to infinity of xn, and that is then equal to limit n to infinity of the expected value of xn. All right, now let's see how we can compute the expectation with the help of the distribution function. And formally, given a random variable, a non-negative random variable x on a probability space omega fp, the expectation is defined in measure theoretical notation as follows. The expected value of x is the integral of omega x omega dp omega. And that is then in limit n to infinity, the expected value of xn. Now, when we're dealing with simple functions, then we know that xn converges from below to x, and xn is basically the sum of ai times the indicator function that we are in the event a sub I, capital A sub I, a simple function. And since x can be defined on a general space, it might be quite difficult to calculate the expectation. However, in many applications, the distribution measure mu sub x of x is explicitly given. So the question is it possible to calculate the expected value of x or the expected value of a function of x, g of x, using the distribution measure mu x, which is a measure on the Borel set? So the question is this possible? And the answer is yes. And the theorem 151, the change of variables theorem, helps us with this. So it allows you to change your abstract probability measure by a more complete one, which is the distribution measure. So let x be a random variable on omega fp, and let g be a function from R to R Borel measurable. Then the expected value of the absolute value of g of x, that is by definition, as we have seen from the previous slide and earlier, in measure theoretical formulation, the integral over omega of gx absolute omega dp omega. And that can now be written as the integral over r of the absolute value of g little x d mu x little x. Yeah, and let's not forget the inverse image of a Borel set is a Borel set. So formally speaking, we should first check whether it's integral. So first we look at absolute values. If equation 1 is finite, then g of x is integrable. And moreover, then the expected value of gx is defined as the integral from minus infinity to infinity of gx d mu x of x. So here we are integrating over an abstract space, and the theorem tells us that this can be achieved by integrating with respect to the distribution measure. We do not prove this here. The proof is based on what we call the standard argument. You can see it in the book and also in the slides to follow, but I will not discuss it here. One usually does this in steps. So the standard argument, one usually does it in 4 steps, where you first assume that g is an indicator function, and you prove the result there. After that, you assume that g is a simple function. So it is, and then we can use linearity to deduce the same result because it's a combination of indicator functions. It was already done for indicating functions in step 1. Then you assume that g is non-negative, and you approximate it by an increasing sequence of simple functions. And then you conclude the same thing by the monotone convergence theorem. You should see it here. That is the line of reasoning. And finally, you split it up in 2 parts, and a g plus and a g minus, and then you can conclude the proof. And the proof is in the book, so look at it in detail in the book. But now what are we talking about? We are talking about this change of variables theorem, and then moving towards the probability measure, right? What are the consequences of this? So let's try to relate it to what we have done before. Suppose x has finitely many values, say little x1 to little xn, with probabilities, the probability that x is equal to xi, that little xi is pi, and that is the so-called atomic measure mu sub x of the element xi. Yeah? And here we have that the sum of I from 1 to n pi is equal to 1. Then for any Borel function g, we can use for x simple functions. So the sum of I is 1 to n xi times the indicator function that x is equal to xi. And that, of course, implies that g of x is the sum of I is 1 to n of g of xi, g little xi, times the indicator function that x is equal to xy. Now taking the expected value of this gx is the integral of gx d mu x of x, and that is the sum of I is 1 to n g little xi times mu x at xi, this atomic measure. And finally, this is, of course, the sum I is 1 to n g of xi times the probability that x is equal to xi. Second consequence, second example, if x is a continuous function, if x is continuous with a density f, so then mu x dx has a density, So mu x of b is the probability that x is in b, and that is the integral over b of x fx dx. This should be a Lebesgue measure, but usually f is Riemann integrable, and therefore it's a Lebesgue integrable, and we can replace the Lebesgue integral by the Riemann integral. So for any Borel function g, we see that the expected value of g of x is then the integral over of gx d mu x of x, and that is the integral of gx fx dx. And as I mentioned, this should be a Lebesgue measure, but in this case, when f is Riemann integrable, we can replace it like this. Next thing, which plays an important role later on, is the notion of risk-neutral measure in financial mathematics. And a risk-neutral measure, we need that later when we do option pricing. A fundamental property here is the use of the change of measure. So we do measure changes. And for this, we start with a probability space, omega fp. And we have a random variable, non-negative, and we name it z. Now we want to use z to change p into a new measure, p tilde. So here's a little tilde on top. If you see it, yeah, there's a little tilde on top. This is a p tilde. So that so if the probability is subject to, if the probability of A is equal to 1, then the probability under the tilde measure of A should also be equal to 1. So sure events stay sure events. And of course, equivalently, when the P of A is equal to 0, then also P tilde of A should be equal to 0. So what are the conditions needed on Z to guarantee that? Well, we have the following theorem. And the theorem has the conditions. It's theorem 161 in the book. Let omega fp be a probability space and let Z be a random variable on omega, satisfying two conditions. First of all, Z is non-negative, so Z is larger or equal to 0, P almost surely. And secondly, the expected value under the P measure. And here we explicitly write that P measure because otherwise we may get confused because we have P and P tilde later on. So here I write explicitly the measure under which I take the expected value. So the expected value under the P measure of Z, that is the integral of over omega of Z dp, that should be equal to 1. Yeah. For A in F, we define then P tilde on F, P tilde on F as follows. Yeah. P tilde of A is then by definition the integral over A times Z dp. This is measure theoretical notation. Measure theory notation, the integral over A Z dp. And this is by definition, so here we have a definition, this is an integral over omega, our abstract space, of the indicator function that we are in A times Z dp. And this is equal to the expected value under the P measure of the indicator function at A times Z. Yeah, so this is, we define P tilde, measure P tilde like this. Then P tilde is a probability measure on F. And for any random variable X, we have that the expected value under the P tilde measure of X And in the book, this is written like E tilde. Yeah, so P disappears in the book. We use that subscript P tilde here for clarity, I think. And in the book uses E tilde of x. That is equal to the integral over omega x omega, little omega, dp tilde, little omega. And that is now equal to the integral over omega x omega z omega dp omega, without a tilde, of course. And if we look at this in detail, we see that this is equal to the expected value under p of x times z. This is a measure change of measure. When x is positive, p almost surely, then we can also look at the reverse. We can look at the expected value under the measure p of x, and we can write this again in measure theoretical notation as the integral of omega x little omega dp little omega. This is now equal to the integral of x over z dp tilde of little omega, and that is the expectation under the p tilde measure of x over z. Yeah, so theorem 161 is an important theorem for financial mathematics, and this z we often call the Radon-Nikodym derivative, but that will follow later. So again, this can be proved, and the proof is in the book. I will not do it here. The statement can be proved by using the standard argument again. So again, one starts with the indicator function and observes that when x is the indicator function for b, then one can write it as follows. The expected value under the p tilde measure, we can rewrite it as follows, and we can see that for this basic function, this holds. That's the expected value under p of x times z. Subsequently, we take x to be a simple function, and then later we take x to be a non-negative function, followed by putting for x plus minus x minus, and doing the same. And that is the standard argument that is followed for quite a number of these theorems. If z is positive, then p and p tilde are said to be equivalent probability measures. If the probability of A is equal to 1, when A is a sure event, that this implies that the probability p tilde of A is equal to 1. Equivalently, when PA is equal to 0, then also p tilde A is equal to 0. Now let's come up with an example. Suppose x is a standard normal random variable on omega fp. And because it's a standard normal, we have all the information regarding the distribution measure. And we can write that down. So that is written down here. The p of x in A, that is the distribution measure, mu sub x of A. And we know that for a standard normal, that is the integral over A of 1 over the square root of 2 pi e to the power minus 1/2 x squared dx. And this is well known from earlier courses in probability theory. And note, of course, that the expected value of x is equal to 0, and the variance defined as the expectation of x minus the expected value squared, that is equal to 1. Now, let's consider another variable, a shifted variable, a variable which is shifted by a parameter theta. So y, let y be x plus theta, and theta being positive. Then, of course, under p, the expected value of y is equal to theta because the expectation operator is linear and the expected value of x is equal to 0. And the variance doesn't change under such a shift. So the variance of y is equal to the variance of x, and that is equal to 1. Now we want to change from p to a new measure, p tilde, which is then equivalent to p, such that under p tilde, this y, this changed y, is a standard normal random variable. So in other words, under p tilde y equal to y in b is then should be the integral over b of 1 over the square root of 2 pi e to the power minus 1/2 x squared dx. And we often write the standard normal density function as phi x, little phi x. So what we see here, that this is just another way of writing, and the book uses it this way. This is then the integral over b of phi x dx. That is the same. And that is then also the distribution measure of the variable under the new measure, the tilde. Yeah, the distribution measure for b. So we want to change from p to p tilde in such a way that we change the distribution to y being a standard normal random variable. To do this, we first define a random variable z on our space omega fp, and we do it as follows. We say z of little omega is e to the power minus theta x, little omega, minus 1/2 theta square. So we choose this z e to the power minus theta x minus 1/2 theta square. And we see what this will bring us. First of all, we have to look at the properties, right? We have to look at the properties of this z, because we had some properties in, let's see, where are our properties? Here we had our properties. Z should be larger or equal to 0, and the expected value under measure P of Z should be equal to 1. So let's see if these properties are satisfied. Well, it's an exponential function. So it is here, it's an exponential function. So it's positive, right? So Z of omega is positive for all omega in big omega. Then the second one, we have to check the expectation of Z under P. And then we use that function G, which is then e to the power minus theta x minus 1/2 theta squared. So let's substitute that. But let's look at E, the expected value of Z. And that is then, in this case, the expected value of G of X. And by definition, that is the integral from minus omega to omega of G of X phi X dx, right? It's under P. And let's not forget our P looks like this, right? Our P looks like this. So it's under P. So this is what we get for the expected value of G of X. And we can write that out. We know our G. It's written down here. We know our phi. And then putting them together, we end up with 1 over the square root of 2 pi, which we can take out of the integral. The integral from minus infinity to infinity, e to the power minus theta x minus 1/2 theta squared minus x over 2 dx. Well, what we do now is just plain calculus, right? We take the minus sign out. We take a half out, and then in brackets, what remains is x squared plus 2 theta x, because we have taken the half out, plus theta squared dx. Yeah, and luckily for us, this is a square, we can complete the square. Luckily for us, this is x plus theta square. So this line to this line is identical, of course. So that's e to the power minus 1/2 x plus theta square dx. Now we do a change of variables. We say x plus theta is equal to u. And that means that dx is equal to du. And in the end, what we end up with is e to the power minus 1/2 u squared du, 1 over the square root of 2 pi. And indeed, we know, right, from standard normal random variables, from the standard normal density function, that this is equal to 1. Right? So both criteria are satisfied. Both properties are satisfied for Z. So Z satisfies the hypothesis of theorem 161. Now we define the probability measure as P tilde of A of the integral over A of Z dP. A is in F, in the sigma algebra. Now to show that Y is standard normal under P tilde, it is sufficient to show, in fact, that the probability P tilde of Y being less or equal to the value little b, by definition, this should then be the integral from minus infinity to b, 1 over the square root of 2 pi, e to the power minus 1/2 u squared du. When this holds true, we have shown that Y is a standard normal, normally distributed random variable. So let's consider it. Let's write it out. So this probability P tilde of Y less or equal to little b, that is the integral of the indicator function where Y is less or equal to little b dp tilde. And we can rewrite that into the original measure. So this is the integral of this indicator function, y less or equal to b z dp, and we call that the expected value of some function h of x. And this is just, we name it this way. Expected value of some function of h of x. Now we write it out. It's 1 over 2 pi. The indicator function, we go back from y to x. So the indicator function that x is less or equal to b minus y. We do a change of variables. So y is x plus theta. It's not even a change of variables. Y is x plus theta. Times the z, e to the power minus theta x minus 1/2 theta squared, times dp, e to the power minus 1/2 x squared dx. Putting this all together gives us again, right, this indicator function gives us an integral from minus infinity to b minus theta, e to the power minus 1/2 x plus theta square, right? We're completing the square, dx, and that is equal, in fact, to, after a change of variables again, from x plus theta being u, dx being equal to du. This is equal to 1 over the square root of 2 pi, the integral from minus infinity to b of e to the power minus 1/2 u squared du. And here we recognize the distribution function of the standard normal, the distribution function of the standard normal. And indeed, we have concluded that the integral, that the probability of p tilde of y is indeed the standard normal. Yeah, so we have shown that y is standard normal under p tilde. And that concludes today's lecture. We have some exercises for the working college. So the working lecture, and we suggest exercises 1.1, 1.4, 1.5, 1.8, 110, and 112. And these last two, they concern changes of measure. So I wish you a lot of success with these and see you next time.